M3, Lab Project M3, which really is the next step. First, you did a project. You downloaded it. There were no programs in it. You added nothing. It was just the bare bones data structure, information, wireframe for the controller, whether it's a real controller or the simulator. In the next lab project, M2, you actually wrote your first rung of code, your first rung of logic, and we more or less tried to exhaust the relationship between a rung of logic and the memory locations in the controller. Now at this point, we've really not done anything with I/O, inputs or outputs. Remember, those are global variables, and those bits of memory are more or less directly connected to screw terminals in a sense. But we're still not there yet. We're not doing I/O yet. What we're going to do in this lab project is we're going to explore the relationship of multiple rungs of logic. In other words, is there any relationship to the order they're scanned in, etc. So we are not yet to the point where we're going to actually use I/O, but a very important thing in this lab project is for you to see that whether it's memory locations that are controlled or effect an output, the code, the ladder logic, exercises and executes totally within that data table structure, those memory locations, aside from inputs and outputs. Totally irrelevant. Everything that takes place in a PLC, a PAC, an industrial controller, takes place right in random access memory. The program's in there and the results are all in there. It all executes within RAM. Inputs and outputs, that's another story, and we will get to that. So let's jump in here. Remember, you can pause right now and do the lab project or do it over, or you can continue, then do the lab project, and then come back and watch this over. But again, for these first dozen or so lab projects, absolutely do not go to the next one if you're not 100% sure about what you did in the last one. That's insanity, because you're just going to get down the road to a practical application with conveyors or some other application that we're doing, and you're going to go, why is it doing that? Well, then you're going to have to go all the way back to these early lectures and do them over again. So just take your time. I guarantee you, you won't be happy if you don't take your time and learn this as you go. So let's jump in here. So far, we introduced you to the simulator, and you see it's been turned on. It's not powered up, but it's turned on in the sense that it's been created in memory. We also discussed the relationship between the memory locations that represent the state of input screw terminals and the state of bits of memory that will be converted to the screw states of output screw terminals. We created a rung of logic. We demonstrated the difference between what you see in the run mode and program mode, online and offline. And of course, if you look on the screen here, I've opened up the various tabs and unpinned them. In case you need a review on how to do that, you simply go up here, toggle pin status, and then the pin basically stands up straight instead of laying on its side. Then you can drag it off to another place on your screen. And I have just enough of the microwave 50 over here in the upper right hand corner so you can see the screw terminals, but we don't need to see those. All we need to see really is the state of the controller, and maybe if we want to connect or look at the communications path. Then down here we can turn on the controller, in other words powered up, and it's defined as being at 100, 100, 110, which is the IP address of your computer, my computer. And because it resides in RAM of my computer, then it is actually at 100, 110, even though Connected Components Workbench is also at 100, 100, 110. Over here I have the global variables opened up over on the right, and I have the local variable. In one of the labs we created two local variables and we moved them into the global variables. That's to make sure you have access externally to them. It's irrelevant at this point. Kind of sneaking up on this whole thing. The next thing we're going to do in this lab is we're actually going to speak more specifically about ladder logic diagrams. By now, you should have a reasonable grasp on the behavior of memory locations relating to inputs, outputs, and in general. My second bit and my first bit, neither one of those are memory locations associated with an input and output. They're just bits in memory. And the only access or control that you have over this rung right now, if we were in the run mode, is you can toggle this bit, my second bit, you can toggle it on or off, and that will then control the state of my first bit. So now we're going to go a little bit further. We had just one rung. Now we're going to go to having more than one rung, so you can see the relationship between rungs. Because remember, when the processor scans, it goes out and collects all the inputs, a snapshot of all the input screw terminals through opto-isolators, and stores those states in memory. And of course, that gets updated at the beginning of every scan. The second thing it does after the input scan is it goes down through the logic, and it goes down and reads, if you want to say, or states the rungs, one rung at a time, left to right, top to bottom. So there's an order in which these rungs of logic are scanned. That's what we're going to kind of get into right now. Then at the end of the program scan, in other words, executing all the rungs of logic, then it updates the outputs. However, if our rungs of logic are not writing to any of the bits like IO, embedded, digital output 0001 that you can see over on the right, if we're not writing to any of those, then there is nothing to update the outputs. They still get updated, but they get updated with zeros, or you're off. First thing we did was we added a rung. So I'll drag down a rung here, and I had you put it on top of the other rung. Now this gives us a challenge here, so we're going to have to stretch down our window, and it's going to cover up part of our simulator. So when you want to work with a simulator, if you just click on it, it'll pop back up on top. And in this rung, and we can do this from the toolbox with a direct coil. Now I see the plus, so you see two plus signs. You let go, it's going to say, what do you want to call this thing? Well, we want to call it, we're going to call it bit 2, and we're going to rename our two existing bits. So I'm going to go ahead and create new tags. I'm going to make it controller scope. This up here, you could pick if there was something to pick there. There's nothing to pick there. Down here there is. I'm going to go to global variables, and I'm going to create 3 new tags. Bit 1, and by default it's going to be Boolean. Hit enter. Bit 2, enter. Bit 3, enter. Bit 4, enter. And bit 5, enter. So I just created 5 Boolean variables, but there I created them in the user global variables, not in the local variables. At this point, it wouldn't make any difference. Here, my philosophy is such: I create everything in the user global variables when I'm writing a program. The only time I put them in local variables is if I come to a point where I know I don't need access to them from any other programs or for any hardware external to the controller, like an HMI or some other piece of equipment. You can always move them, because we showed you in an earlier lab how to move, copy, paste, and then go back and delete the old ones. You could do cut and paste. It makes me a little nervous if you cut something and then if you slip of the hand and bang, it's all gone. So I typically do copy, paste, then I go back and delete. You also saw in the previous lab that when you do that, if there were instructions that were addressing those bits, they can no longer find them at the path they were defined at. So if I move them from the local to the global, and the logic was written looking for them in the local, you have to go to the variable selector and kind of reselect them and repoint the instructions to read it in the global instead of the local. Or if you move some from the global to the local variables, you have to go through that same process. I've created bits 1, 2, 3, 4, and 5. If you look in your lab project, in one of the very early steps, it has you setting this to bit 1. I can just click on that, and I can go up and select bit 1, like that, and this would be bit 2. Or I can just type in B and click bit 2. And up here, type in a B. So it's type ahead. Next, I ask you to download. We need to turn on this controller, this simulator, because if you're trying to download to an actual controller that's not plugged in, no power on it, RS Links isn't going to find it. So we turn it on. Now we have a controller. It's a simulator, but to CCW, it looks like a controller out there somewhere at 100, 100, 110. We're not connected with it. We're not online with it, but it is connected in a sense. So now we want to download. Up here, you have build and you have download. If you click on download, it's going to build. So I typically never use build unless I want to check the syntax of the code. In other words, you know, here's my code right here. I don't see any warning signs, so I'm assuming it's okay. If I build, all that I'm going to get as a result is it's going to say, yeah, everything looks okay. If I click on download, which I'm going to do, it's going to build first. See down here? Build started. Build succeeded. 1 succeeded, 0 failed, 0 up to date, 0 skipped. So, in other words, no errors, no warnings, no foul. Now it's continuing to download. Now, it really doesn't matter if I download with project values or just download without them. So I'll just hit download. You could say that we have the states of bits 1, 2, 3, 4, and 5, and they are 0, and we downloaded the program with them at 0. But the controller, the simulator, did not have bits or bit 1, 2, 3, 4, 5 in it. So it's not changing anything down there. So we downloaded, okay, here's your, you get 10 minutes. If you didn't buy the developer edition, I get 24 hours. Honestly, 10 minutes isn't bad. Here's the thing that I hate, and I don't know any way around it, like saving a workspace or something. All this comes up, and I really want the global variables to show over here somewhere. So this isn't the same order I had them in, but I'll just put them over here again. And I do like the Micro 850 tab. I do like that to display over here. And of course, every time we go offline and then re-download, this is all going to disappear. I don't know any way to fix this. Hopefully, at some point they'll have a save workspace or something, so we can just pop back up with it like this. Now I'm going to collapse this up a little bit to expose the power button and the IP address. So you see we're in the run mode. In the instructions it told you not to go to the run mode. Oh, wait a minute, we're in the program mode. No, it says run mode right here. I'm going to go back to the program mode because that's what it told you to do. Okay, and this is what you would have seen. There wouldn't have been any difference at this point. So I apologize for letting this go to the run mode immediately. Where in the lab project it said download. Oh, it does say download and go into the run mode. Oh, we're in the program mode, and that's where we're going to do it. To reiterate, that was a mistake on currently page 88, the beginning of the M3 lab project. Down there in step 3 it says download and go into the run mode. That should not have said and go into the run mode, because immediately below that I'm saying select no for going to the run mode, because I wanted to show you what you see right here in the program mode. You can see over here we're in the program mode over here in the Micro 850. This looks true, and it is. It's unconditionally true, but you're not turning on bit 2. Down here this is false, and of course, so this is false, and you're turning off bit 2. So in looking at this, you would not know whether this was in the run mode or not, because this is the way it would look in the run mode, because last man wins. And that's something we need to emphasize now that we're talking about ladder logic diagrams and we've gone beyond one rung. We have 2 rungs here, both of them addressing bit 2. The first one would say, hey bit 2, you're on. The second one, because it's false, would say, hey bit 2, you're off. But we're in the program mode. But again, this is exactly how it would look if we went to the run mode. And the questions, the instructions are always true or false, but never on or off. Understand this or it will hinder your ability to work with ladder logic diagrams. Is rung 1 true or false? It's true. In the run or the program mode, it reads true. It's not executing right now, so it's not executing true, but it reads true. While watching the output on rung 1, which is bit 2, switch the controller to the run mode, and we'll do that over here, run mode. And you notice nothing changes. We switched it to the run mode. Is rung 1 true? Yes, it is. It's unconditionally true. Why is it not controlling the physical value of bit 2 to the on state? Well, rung 1 turns it on and rung 2 turns it right back off. Last man wins. Then we had you disconnect. Now you can go up here and click on connected and it will disconnect. Or you can go over here and click on disconnect. I know that might seem confusing, and I'm not sure the efficacy, if that's the word you want to use, the effectiveness of doing it this way, but I'm just going to click there and it's going to put it into the offline mode. In other words, we're looking at what's offline. We didn't upload anything, okay? But we didn't change anything online either. So there was no need to upload it before we went offline, because this is the entirety of our logic and there are no values because these were, bit 2 was off when we went offline. So we had you disconnect and then we had you swap the 2 rungs. Okay, and it doesn't matter whether you bring 1 down or 2 up. I'll just bring 2 up. See, now they're in a different order. So now they're being scanned in a different order. Then we had you download. That does take a minute. And I'm just going to download not with values just because it's slightly quicker. Now, here it says to download and run. Okay, so I'm going to add an extra step here and I'm just going to say no. So it goes online, but it's not running. And then, of course, I'm going to delete the output window here. I'm going to turn it off. Now, I could drag that output window down here because remember, it has a pen status. We're in the program mode right now. And the lab told you go to the run mode. But I decided to add another step in here is to not go to the run mode and look at this. The first rung is false and it turns it off. The second rung is true, but it's not turning it on. That's because we're in the program mode. Now let's go to the run mode. And look, it flipped. Okay, rung 1 is false, but bit 2 is on. So if you were looking at this, you might think, well, wait a minute. If this is false, then how come that's on? Well, right below it, it's unconditionally true. And it wouldn't matter what was in here. If this rung is true, it's going to turn on bit 2. This rung is false, it turns off bit 2. But the program scans rung 1 before rung 2. And then when it gets down to the end, bit 2 is going to be in the state that it was last told to be in. This rung says you're off, this one says it's on. Last man wins. Very important characteristic of ladder logic diagrams. Then we had you switch it back to the program mode. And the reason that nothing changed here, remember we were in the program mode before and it was the opposite of this. Well, meaning that bit 2 wasn't on in either one of these rungs. But when you go from the run mode to the program mode, the last scan before it switched to program, it told bit 2 to be on. Now see, if we swap this all back around, because remember we swapped these 2 rungs. And with the rungs swapped, you ended up with the opposite state for bit 2. So if we went back and repeated that, you would see what I'm talking about is when you go to the program mode, it's going to show you the last state that it was in, not what it logically should be when you read the rungs, because they're not executing. Then we had you toggle bit 2 off in the program mode. Toggle bit 2 off. Okay. And then toggle bit 1. The question in the manual was, looking at this, what mode would you say it was in, the controller? Now you can look over and see it's in the program mode. But if all that you could see was this, what conclusion would you draw? Both these rungs are true, but in both cases it's showing bit 2 is off. This is the same bit. There's only one bit involved here, bit 2, in both cases. The true execution will turn bit 2 on here or turn it on here. The moral of the story, which we will eventually get to in this last man wins situation, is you never use 2 OTEs addressing the same bit in memory. It's called a destructive bit. So the logic never works out right when you do this, but we're using this to illustrate the nature of ladder logic diagrams. In other words, between 2 rungs and the order that they're scanned in. What do you expect to see to happen here when you switch to the run mode? So let's switch to the run mode, but you tell me what you think is going to happen. Well, I can tell you what's going to happen. Bit 2 is going to be on. That's what you should have expected. Now the lab told you to disconnect and add a true if off instruction into the second rung. Now I can do it from up here by taking a reverse contact, dragging it over here and dropping it, and then assigning it to bit 1. And then we had you reassign the variables. These are both bit 1. We want to leave these both bit 1, but over here we want bit 2 and bit 3. Now we already created the variable bit 3. So there's a variety of ways that I can do this. I can click on this and just hit bit 3, or I could have gone into kind of an edit mode. You don't want to edit the tag. The tag that was there before, we don't want to edit that one. We want to assign a different tag. Regardless, this is what we had you change, and then we had you download. So I go up there, click on download. This is going to take a minute. I'm going to download with project values rather than have to think about what I want online and offline. Just for grins, I didn't have you do this in the manual, but I'm going to unpin this, but drag it down here so it doesn't keep popping up in my view, because I really don't want to see it. So this won't pop up anymore in front of our logic. Okay, so we are in the run mode, and I had you toggle bit 1. And then I ask you if both of these rungs could ever be true simultaneously. And the answer is no, because bit 1 is either on or off. If it's on, this rung is true. If it's off, this rung is true. So both rungs can never be true simultaneously. Then we had you disconnect again and add an additional true if on. Now I'm going to go to the toolbox because I want to make sure that you know how to do this from the toolbox. It's going to come up and it wants a memory location, and that's going to be bit 4. So I can go here and double click on bit 4. Then I'm having you add another true if off reverse contact here and making that bit 5. Now I don't want this here, so I'm going to click here and make it disappear. If I hit the X up there, then this would disappear from your workspace. We don't want to do that, but we want to download, and the step says download to the controller, and then it says to click on no when we get to go to the run mode. Now if we left it in the program mode, it won't come up asking us if we want to go to the run mode. No, we want to answer no because we want to see what this logic looks like in the program mode. That's interesting. Oh, there, good. It popped up here. The output window here, it popped up, but then it jumped back down to where I put it. That's good. I didn't have you do this in the lab project manual. And when you're writing code, you don't have to spread all this stuff out like this. We're just doing this to clarify what we're doing. So when we look at this logic, can you say by looking at just the two rungs if the controller processor is in the run mode or the program mode? You know you're online because you're looking at the kind of pale yellow background with the blue and the red. So we know we're online. We're animating what you're looking at offline. This ladder logic, these two rungs, it's offline. But the data is online. The state of bit 1, 2, 3, 4, and 5, the online state in the controller, the simulator, is being used to animate the color of this offline graphics. So if you were going to, someone's going to ask you, look at these two rungs, if it's program mode or run mode. Well, you can look, the first rung's false and bit 2's off. The second rung is true and bit 3's off. Therefore, it's in the program mode. It's not executing. Then I had you toggle the state of bit 1. It doesn't matter whether you do it here, or you go into your variables and do it. We'll just click on one of these, toggle Boolean value. Okay. Now neither rung is true, but we're still in the program mode, right? Now we switch to the run mode. Okay, both rungs are false and bit 2 and 3 are off, correct? Let's go to the run mode and execute these two rungs of logic. Did anything change? No. So looking at this state of these two rungs, you can't tell whether you're in the run mode or the program mode. Now you can tell by looking other places on this, like over here, you can see you're in the run mode. But looking here, you can't tell. But if this were a real controller, it might be in a control cabinet and you can't see it. You always need to be aware of how the logic looks on the screen and whether it's in the run mode or the program mode. So you put it in the run mode. Which instructions are true? Direct contact bit 1, right there. Yes, it's true because it's red. Direct contact bit 4, it's false, or it's false. So bit 1, read bit 1 on, true. Read bit 4 on, false. Now, if you read this one, it's false, and if you read this one, it's true. On the next page, we ask you again, not about true and false, but on or off. Now, I included all of this stuff, so let's look at them one at a time. Looking at this instruction, is bit 1 on? Yes, it is, because it's true. Looking at this one, is bit 4 on? No, because it's false. Looking at bit 2, is it on? No, because this changes color directly in response to red, it's on, blue, it's off. But see, here, red is true, blue, it's false. This is true, false. This is all true, false, and this is on, off. Bit 1, looking at this, is bit 1 on or off? Well, you know it's on because this is false, right? It's true if it's off, but it's false, therefore bit 1 is on. Looking at bit 5, is bit 5 on or off? Well, it has to be off because this is true if off. So you need to dwell on this extensively until you've firmly got in your mind how to read just a couple simple rungs of logic. And the only real convolution we have here is that we're using a true if on bit 1, a true if off bit 1, because we want to clarify the difference between two different instructions addressing the same bit in memory. So in rung 1, it says bit 1 is on. Therefore, it lights up red because it's on, true if on. In the second rung, it says bit 1 is off. But because it's on, it comes up blue and false. And that's pretty much what we did in this lab project. Was we went from one rung to two rungs. We went from multiple conditions or permissives, the true false stuff, to see how it affected the state of the bits addressed by the OTEs, or the direct coils, if you want to call them that. Because remember, these have a true and a false execution. This instruction does something to bit 2 if the rung's true, and something different if it's false. I would say that the single most important thing that you learned from this lab project, M3, was last man wins. If you are in a line with your fellow employees or buddies, and someone's asking you what you want for lunch, and they go down through the line and ask everyone, they get down to the last person and they say pizza, then you're having pizza for lunch. Everybody is. Last man wins. Last man standing. Remember that the previous lab was one rung of logic with two instructions, two memory locations. We exhausted that relationship. This lab project is two rungs of logic using the same memory locations, more or less, and then flipping the rungs around to produce something we call scan-dependent logic, meaning that if you put the rungs in a different order, in other words, you take the two rungs and flip them, you're going to get a different result. Now, you don't want to write code that way. You don't want scan-dependent logic. There are situations where you can't avoid that, and we will demonstrate some of those in later lab projects. When those cases come up, you want to make sure that you put all of that logic that's scan dependent into one rung. That way, if the rung if it gets moved around, it's not going to hurt anything because the scan dependency is embedded in that one rung. That's a subject for another lab project. So that's what you should walk away with from this lab project, is the relationship between multiple rungs of logic and the bits in memory that they address. So thank you for your rapt attention. And we're going to close this up, and we'll see you in the next lab project.